So if you have an empty seat next to you, raise your hand. So the people on the side will see. Why don't you move into this seat? I don't want people ideally on the stairs. If you have an empty seat next to you, move into it. Yeah, over there. Move. The row below also. Why don't you move? Move. Okay. There's one here too. One more seat here in the second row. Why don't you guys move into it? Okay, so let's start. I'm going to try to make to start every time at 10:33, and I'd appreciate if you be here at 10:33. I know that people are either coming from classes or waking up, but 10:33 is reasonable, so we'll try to make it. Okay, so welcome. Hopefully you had a good weekend, long weekend. And we're back to 519. So let me start by quickly recapping what we've done last time. Can you all hear me at the back? And I tried to change the lighting a little bit. They changed the system here, so I'm not sure what's the best. But if it's too bright or something like this, let me know. We can play with it again. Okay, so that's the class. I discussed it last time. This is just to give you a recap of all the topics we're going to cover. You know the time. We have a lot of TAs, so you'll have a lot of people to ask questions to. There's 5 problem sets plus homework 0 that you all know about, which is mandatory, which means everyone needs to submit homework 0. If you're on the waiting list, I'm going to say more about it a little bit later, do the same. If homework 0 is not for you, too difficult, too easy, uninteresting, then it's a good time to know now. As most of you know, we had some problems with Canvas. Now it's okay, but we extended homework 0 until the end of this Friday, so it should give you enough time. We are going to have weekly recitations twice a week, midterm project for people that are in 519, and optional for people that are in 419, and a final. This reminds me of the project, among other things. I'm going to talk about it today. This could be a great project if people want to do it. This is a machine learning problem, learning how to file my emails into folders. Apple is doing a pretty bad job. I think you can do better. So, okay, so registration. I think this is on, yes? That's okay. Yeah. So registration. So we have now about 30 slots in the class. About 20 of you should receive today, 20 of the people on the waiting list should receive today messages that are in the class. A few of you probably already received it yesterday. And we're going to make progress. There's still a long waiting list, but I assume that some people that registered early to the class will decide to drop it. If you are like that, or you know someone who is registered to the class and isn't here and is taking something else, please urge them to do it quickly, because it just slows the process. I know that this happens every year. It just slows us down. But if you are on the waiting list, just pretend that you are not on the waiting list and you're just taking the class. Come to classes, do everything as if you're on the class. Nothing is going to prevent you from doing it. Everything is going to be open once we are completely done. The website is going to be one of the places where everything is going to be eventually up to date and announced. Piazza is another place. Please go on Piazza. The pointer is on the webpage, which you should be able to find. I know that many of you are already there. Okay, so I'm expecting that you know all this, and to some extent, homework 0 will kind of refresh your memory or tell you whether you know it or not. I'm expecting that you've done some Python. Next Monday, this coming lecture is going to be devoted to an introduction or refresher in Python, and specifically some of the packages that you'll be using in the class. Please come even if you think that you know Python. I think it's going to be useful. In fact, even if you know Python, come and ask questions, because that's going to help all the other people that are less fluent than you. The recitation next week are going to be devoted to Python. So please go to this. This is going to be announced on the website and on Piazza. Homework 0, I talked about it. I don't expect that you'll just sit down and do it in an hour. Would be nice if you can do it. But I do expect that you spend a few hours on it, you look up a few things, and eventually you can do at least 2/3 of it. If you cannot, it means that you should come to this class next semester or next year. Okay. I already said it last time, and I'm going to say it many more times. I really want this class to be as interactive as possible. Ask questions, respond to my questions, comment. It's important to me to understand what you get, what you don't get, how you think about things, what's the terminology gap between us. And the only way for me to figure this out is if you say something. And as I said last time, just a second, whenever you have a question, comment, misunderstanding, half the people around you have about the same question, comment, misunderstanding, so you're helping them by not being that shy. Yes?
As homework 0 graded?
No. We're just going to look at it and see that you've done it or what percentage you've done. We're going to give you solutions. Also, at the end of class, typically there's going to be 20 people standing here. 18 of them are asking the same question. And you can imagine, what kind of questions people have at the beginning of the semester. Please ask it now, or just before the end of the class, I'm going to give you a chance to do it. Yes?
You mentioned that the Canvas issue was resolved. I checked and it's still not added.
When did you check?
Before class.
Today?
Yes.
Okay. Other people have the same problem?
Yes.
Okay, we'll check again. So I don't know. I mean, I know what happened first time. They kind of, by mistake, canceled our canvas after they generated it. They regenerated yesterday, and it looked okay. So I'm going to check again. Thanks. But if that bothers you with homework 0, basically send email to Hang Feng, who is the head TA. We'll try to resolve it. There was another question here. Same issue, Canvas? Okay. Yes.
I'm answering some questions on homework 0. Is that okay, or do you want us to answer all the questions?
Try to answer all the questions. If you cannot, answer whatever you can. Yeah, but really it's called homework 0 because it's pre-class homework. It's for you. I want you to refresh your memory, to look around, to try to do things, and make sure that when we start doing even notations that hopefully we'll get to today, it doesn't bother you to see a slide that has some math notations on it. Other questions? Okay, so another thing I want to mention, this is an applied machine learning class. And it's applied because you're going to solve problems that we try to simulate what you will do next year or in 2 years when you try to actually solve problems in industry. We're going to give you data, we're going to ask you questions. Each problem set is going to be a small project. This is where the apply is. In class and in quizzes in the exam, it's going to be the machine learning, the background, all the information you need in order to understand what machine learning is and why does it work, and when does it work, and why it doesn't. There is this dichotomy between these two parts. You'll see it all the time. Don't tell me at the end, the professor didn't say that the exam is going to be different than the homework. It's going to be different than the homework. But you're going to see enough of it during the semester, in the midterm, and in the quizzes. Okay, so I already talked about the policies. I'm just going very quickly over it. We talked about this. This was the policy. And I also said that we're taking it very seriously, as everyone does. Collaboration is encouraged. I mean, as I said, homework are going to be time-consuming and difficult. In general, I think that this class is time-consuming and difficult. I think it's a lot of fun. Many people really enjoy it, but you're going to spend some time. So I encourage you to collaborate on homework, but it's essential that you write your own solution and your own code. As I said, this is where learning happens, where you kind of took all the discussion that you've had and the decision that you've made with your friends, and you sit down by yourself and you write it down. This is where you make sure that you understand. We have a late policy that is very simple. This is the grading. 40% homework, 30% final, 20% midterm, 5% quizzes. If you're in 519, this is going to consume only 80% of your grade, and 20% is going to be the project, which means that it's going to be a big project. 20% of the grade. We're going to talk more about it as we go. Before questions, I assume you want to know how grading works. So from my perspective, today you all have A+ in the class. For some of you, it's going to go down from today if you're not going to do the work. That's how it works. So my experience over the last few years of teaching it has been that the distribution is something like this, from A+ all the way to C, or whatever it is. Something like 35% to 40% are going to get some kind of an A. About 40% are going to get B, about 20% are going to get C. That has been the statistics for the last couple of years. It's going to be about the same because it's a very large class, and statistics don't lie, or don't lie a lot. That's hopefully at least informative. Questions? Yeah.
Is that for 519 and 519 combined, or?
Yes, it's about the same. So as I said, 519 have a big project component that is mandatory. It's part of the grade. 419, if you do the project, it's going to help you. And a lot of people last year actually did nice projects and it helped them. So the distribution is about the same. Yeah. We'll see what happens. So I typically prefer to do a short final, if that's what you... So there are two parameters. One is the length of the final, and the other one is whether it's comprehensive. It's going to be comprehensive, but I don't want to do it 3 hours or something like this. You don't want it to be 3 hours, so I'm going to try to make it a little bit shorter, but it's comprehensive. Yeah.
For 419, and we do the final project, will it also count for 10%?
Yeah.
The same way?
Yeah. Only if it's improving your grade. So 419 students can only gain from doing a project. Okay, so website, I assume you all know this. Okay, learning. So last time I gave you this small puzzle, and some of you solved it in a few seconds. Hopefully some of you looked at it later and thought about it. It's really an example of the key learning protocol, the one that we're going to spend most of our time on, supervised learning. However, it's an example of many, many other things. And the first question I ask you, and I want the answer again, is, without telling me what's the answer, are you sure that you got it? And I think several of you were sure that they got it. Why? Yeah.
They mentioned they didn't find a counterexample.
Okay. So one answer was, it's consistent with the data. I wasn't convinced by that, because this is also consistent with the data. I can use this as my function, just the list of all names with pluses or minuses, and that's also consistent with the data. So that's maybe essential, maybe almost essential, important, but not sufficient. Yes?
It was also generalizable, so if you had new data, you'd be able to like,
So it has one property that this solution does not have, that it's some kind of a function that you can apply it on new instances and decide whether you or you or you are plus or minus example. That's an important property. But still, it's not sufficient to say, to convince me that you're correct. You have a function. How do you know that this function is correct? Yes?
You can never fully know because it's possible you can always get a new name and it doesn't match your function.
True. Nevertheless, a few people here were very convinced that they got it. Why? Yes? It was simple. And even though this, you can argue against this argument also, people stopped looking once they said, I have a very simple explanation. It explains hundreds of examples. Must be right. And this is a good intuition that we're going to quantify and, in fact, prove around the middle of the semester. It's actually something that is important and, in some sense, drives learning. So this is one important thing that we learned from this example. But there's a lot of other issues. So what was the function that is behind this? Yeah?
Check the second letter of the first name.
Second letter of the first name, check whether it's... Okay, so what is a vowel? Okay, so you give me a list of characters, but vowel is not in the input. The input has characters, N, A, O, K, I, A, B, E, and so on. Vowel is not listed there. So what's going on? I mean, you gave me a function that is not function of the input. It's a function of some information you brought from home. Some knowledge. Is this knowledge important here? So let's assume that I'm replacing this function, and instead of A, E, I, O, U, the function is going to be the second letter of the first name is either X or Z or B or D or K, which is as complex as vowels. What would be the impact of that? Yeah.
You'd still be able to identify, like, you would still be able to, like, identify the pattern, but you wouldn't have as much of an easy time interpreting.
Okay, so you're saying two things. One, you would still solve the puzzle.
Yeah.
Would it take you less time, more time?
It would take you a long time, because you're basically one hot encoding every letter, and then trying to figure out whether the presence of that letter.
So somehow your background knowledge help your search in the space of possible functions. Also, it help convince yourself, or all of you, that the function you found is good because of the simplicity. But think about the fact that really background knowledge played a huge role here. Now, there's another thing that has to do, many things we can say about representation. I told you that the real story, it's written here, was that people had their plus and minuses on their badge. I simplified the problem for you here. Everyone agrees that I simplified the problem? Why did I simplify the problem? By putting all the names on one place rather than you have to look at the badges of all participants. That's one. Two, yeah? Right, so that has to do with the representation. Let's assume that you decide to encode the information on the badge by measuring the shoe size, the height, the country of origin of the person, and you did not take the name into account. It's a solid representation of the information. It won't help you because the function doesn't depend on it. So what you take from the input, how you represent it, how you encode it, what you give to your learning algorithm is crucially important to what's going to happen. And there's a few other things that we can talk about. I want to just mention this last bullet here. When did learning take place? So I pose this as a learning problem. Yes?
It take place in the class when you were looking at the list?
Okay, that's one option. So you're looking at the list, you said positive example, negative example, let's find some function. Is that the only time it took place? Yes?
Because our answers were influenced by the background knowledge whenever we learned about vowels.
So you knew vowels. Without the knowledge of vowels, you wouldn't have got it, at least not in class. Would have taken you a lot more time. So some of the learning, some representational issue, right? Some mapping between characters to the notion of vowel happened years ago. You brought it here, you used it. So you did some, let's call it pre-training, before you even knew I'm going to ask you this question. Without that, probably would have been harder. So that's, again, something to keep in mind. How would you write an algorithm? Now you have to, we are computer scientists, here's data, write an algorithm that outputs the function. Any ideas of what would you do? Yeah?
Maybe a first step would be to replace the letters with corresponding numbers.
Okay, so you will have some encoding of the letters. And then,
Presumably we'll learn about that in the course, but if there's a number of algorithms, you could then plug that into.
yeah, but before plugging that into an algorithm, you'll have to think about what is the real input here. That's what I want you to think about. So I gave you strings. If you just give this string as input to your learning algorithm, whatever learning algorithm that is that's going to be sufficient. There's almost no way you can think about it this way. You really have to think about what matters. What in the input matters? How do I encode what matters? We're going to call these features, representation really, and only then the learning algorithm is going to work. And as you will see, and I already mentioned it before, representation is crucially important, perhaps more important than the algorithms. Okay, so that's where we are. So now that we are done with this, we can move on to try to understand learning. And the first thing I want to do is I want to introduce some terminology. You've seen this list before. This was your training data. Training data is going to be a collection of input with labels in the supervised name. For example, here is one positive example, one negative example. And then you may get in the application some raw test data. You want to know whether Shivani, Lyle, other people that you may know here are positive or negative according to this function. So if I give you some label test data, this is going to be used for you as a way to evaluate how good are you doing. Okay, we talked about this. And so basically what are we doing? We're playing a game that is called supervised learning, where we are looking for a function. We are assuming that there exists some function f that maps item x to labels y. Our input is going to be a collection of lowercase x that are elements in what we're going to call an input space or an instance space x. The output is going to be a collection of labels that we're going to call y. And we assume that there is some function that maps x to y's, and we are basically after this function. That's the game we're playing. So typically we're going to use machine learning when this function f is something that is unknown, and we cannot really think about it. We cannot program it conventionally. We really need to write learning algorithms. So spam filter is one example, right? So you really don't know exactly to write a function that takes the email, maps it to spam or not spam, phishing or not phishing. You have some idea what this depends on, which is crucial because otherwise you won't be able to learn this function, but you don't really have a good function that does it. I gave you this example of these three names. Tell me whether they represent the same person or not. Again, you can do it. You have to think a little bit about it. But we don't know how to write a function that takes a story as input, even if the names are already identified in the story, and determines whether they represent the same person or not. It really is something that you have to look at a lot of examples. It depends on a lot of contextual cues, and the function itself could be highly complicated. So these are the cases where we want to use learning. So again, this is the input, which we call instance space. Output is the label space. And there exists some function, y. We're going to call it the target function. We are going to learn a function. The target function is f of x, the truth. We are going to learn some function g of x. And we're hoping that g is going to be close enough to have. So what's going to do the work is a learning algorithm that is going to take our label training data, pairs x, comma y, in this case, capital N examples, and this learning algorithm is going to produce a function, g of x, exactly the same function that you produced just a few minutes ago. The function g of x in this case is look at the second character of the first name and check whether it's a vowel or not. If it is, say 1, otherwise say 0. This is not the only learning protocol. Any other ideas? Yeah.
You could have it randomly generate a function and then modify it based on how it evolves, so to speak, instead of having it learn.
Well, I'm not sure what's the difference between learned and evolve.
Maybe there isn't a difference, but I understand learning algorithm to be you feed in training data, it trains, and then you have a fully functional black box, so to speak. Whereas if you were to have it evolve, you'd have, I don't know, how to have some random inputs, or have some random coefficients to begin with. It spits out some output, it's almost certainly wrong, and then it modifies its own behavior.
Okay, so that I'm going to call this an online learning algorithm, where it starts with something, could be random, could be some heuristics, could be a guess, and then as it sees more and more examples, it evolves, if you want, it learns, and hopefully improves. So this still counts as this protocol, but notice that in this protocol I gave you instances, these are the names, I gave you labels, Ys, for all these, and that was your input. You could imagine cases where the input is different. Maybe I don't give you Ys. I just give you X's. But I tell you, there are some patterns there. Or maybe I give you some of the Ys, only Ys for some of the X's. Or maybe I ask you, you know what, go out to the world and figure out the Ys yourself. And we're going to see even today, hopefully, an example like this. So this is not necessarily the only way. We're going to see a few other ways of learning, learning protocols. But this is the one that we're going to play with most of the class. This g of x, which we are going to call the output, the hypothesis, the model, is the function that we're going to use when you go out to the world and apply what you've learned. When you take your vowel function that we mentioned before and apply it to other names that were not on the list. Okay, so we learned something, yes?
Can you see that is the only supervised learning protocol?
I think that's generic enough to be the only supervised learning. What do you have in mind?
No, it's just confirming that.
Yeah, so that's a generic way to define a supervised learning protocol. Yeah. Okay, so now that we've learned this function g, we want to know whether it's good or not. So typically, we want to reserve some data for testing. This is testing data, or test data. Again, pairs x and y, only that we're not going to see. We're not going to let the algorithm see the y's. The algorithm is only going to see these x's. We're going to take the algorithm, the model that we learn, run it on the x's, produce g of x's, and compare them to the y's. And hopefully, what we're going to see is going to confirm that our g is pretty good. So that's going to be the test stage of our algorithm. Okay. Again, you can ask yourself, here is test data. Can you use the test data otherwise? Because basically what I've done here is I wasted data. Right? I had data. It looked like this. And I did not use it to train my model, potentially to improve my model. I said, well, I have to save it pull it aside because I want at the end to figure out how well I'm doing. So I'm not going to use it for training. So you may want to think about, are there other ways for us to use the test data? And again, we will not answer it now, but something to think about. So now that we have a protocol, we can think about, yes?
So the original goal is to figure out the function of x, right? Not, so when you say we have not learned g of x, does that mean we as the programmer understand the function now, or we just have a model that the computer blindly applies, and we can tell you if the next thing is going to be plus or minus?
Okay, that's actually a very, very good question. So the way, what's your name?
Tricky.
Twiggy, that was the right way?
Yeah.
Says it, do we, as programmer, do we understand the model? This is the key question in machine learning today, interpretation of models. I don't know if we understand it or not. What we do is we have a box that is called g of x. We give it x's. It produces g of x's. So we give it input. It gives us output. Whether we understand what it does, like the vowel rule that you came up with, where we understand it completely, it's besides the point. Maybe it's an important issue, but we're not going to deal with it a lot. Most of machine learning disregards this question completely. It wants to get a function that it can apply on the input. We typically don't know what it means. Now, in many cases, it's very difficult to know exactly what's inside the box or to understand exactly what's inside the box. In many cases, you actually want to be able to know what's inside the box. So that's going to be a question that we will come up a few times, and it's a very, very active research area, trying to interpret the function that you've learned. We're not going to deal with it now. What are we going to do? So these are really the key issues in machine learning. And I'm thinking about it here as divided to three parts: the modeling issue, the representation issue, and the algorithms. By modeling, I mean, here is an application, here is a problem I want to solve. How do I formulate this as a machine learning problem? It has to do also with how to represent the data, how to model the learning process, which involves how to represent the data. It also involves what are the learning protocols that we're going to use. So first part. The representation is the second part. What function should we learn? So I did not tell you which function to learn when I gave you this data. You came up with some function. You were convinced that it's simple enough and good, and that's it. It's not the only function that does that is consistent with this data. As I said, this is another function, this piece of paper, and there are many, many other functions that you can write that are consistent with the data. When you, part of our job is to think about what types of functions do we want to learn. We're going to call this the hypothesis space, the set of functions that our algorithm can use. We'll have to think about how to map the raw input, the names in this list, into a representation that our programs can do something with, and our algorithm knows what to do with. And this is perhaps, or the first two, modeling and representation, are perhaps the least studied issues in machine learning and probably the most important issues in machine learning, because no algorithm is going to work unless you do modeling and representation correctly. And really, as I said, it's the least studied area. There's a lot of intuition, hacking, know-how, and don't know how in the hard problems. And we're going to try to think a little bit about this, talk about it, and see if there are any general principles. And then we get to algorithms, which is people think about as the most fun part, and it is, but it has to be clear that it all builds on the first two parts. When we get to algorithms, we have to understand not only how algorithms work, what do they produce, but also what does it mean to be a good algorithm? How do we define success for learning algorithms? You wanted your algorithm to generalize, but when you said generalize, you meant I want to be able to evaluate it on a new name. But you want more than that, right? You want to evaluate it correctly on a new name. How do you guarantee? So you can come up with a function, you can compute it on any new name, but how do you know that you're going to do it correctly? This list is another function, and it overfits the data, right? Your function may be even wrong on one of these names, but still evaluates correctly on most of new names. So this issue of generalization is important here. And of course, there's a computational problem. We need to compute eventually. We want to make sure that the function, the process of learning and the process of evaluating the function that you learn are efficient enough as a function of something, the number of the examples, the size of the examples, so that we can actually compute it. So we're going to address all these things, and we're going to start again with recapping and notation before I get to modeling. So instance space is going to be the representation of the input, the collection of inputs, and in order to determine the instance space, we have to decide what are the features that we're going to use. Label space is the output. In our case here, it was just plus or minus. In other problems, could be a different label space. Will depend on the learning task that we care about. Hypothesis is going to be the collection of all functions that we allow our learning algorithm to explore. The G's that I had before, the set of all G's the learning algorithm will choose from. What learning algorithms do we use? We'll see that there are many different learning algorithms with different properties, and they will produce different kinds of models. And finally, how do we know how good we are? So we're going to introduce a notion of a loss function or an evaluation metric, not necessarily exactly the same thing, could be different. But this will allow us, one, to measure success, sometimes also to drive learning, because our learning often is going to be, just like was suggested here, some kind of an online process. We're going to try something, we're going to see how good we are based on some loss function. Are we losing a lot or not? And this is going to drive the improvement. If we are not losing a lot, maybe we're done. If we are losing a lot, let's fix something and learn better. So this is some terminology that we're going to use a lot. Let's start with instance space. You already saw this figure. We start with X in capital X. We want to learn a model G that maps it to Y. And really designing this instance space is crucial to our ability to learn. We can think about Boolean features. In the case of spam, is there a folder name after the sender? Or filing email in general? Does the email contain the word class? Does the email contain the word waiting? Maybe I wasted something here, because maybe all the emails that contain the word waiting also have the word class in them. So I don't need two separate features here. But these are Boolean features, right? So this is something that is a property of the input. It evaluates to yes or no. And I can take my email message, convert it to a collection of these Boolean properties, and send this to my learning algorithm. So my learning algorithm is going to see a list of Boolean properties of the email. It's not going to see the email. That's one option. right? So for me, this is a representation of the input. My instance space now is going to be a collection of Boolean properties, Boolean features, rather than the email itself. I can also have numerical features. I can ask, how often does learning occur in the email, the word learning? How long is the email? How many emails have I seen from this sender? This is an interesting feature because it doesn't apply only to this message. It applies to the history of messages. Again, I'm not giving all the message to my learning algorithm. What I'm doing is I'm running some simple functions that I invented myself, this list, on the email. I have a bunch of properties, and this bunch of properties that we're going to call features are going to constitute the input to my learning algorithm. So my instance space is going to be a collection of these properties. You can also think about bag of tokens as an option. Just list all the words in the input. I call it tokens because, as you will see in one of the problem set, just identifying all these words is not a trivial thing, and it's sometimes an ambiguous process, so you have to decide exactly how you do it. Let's go back to the badges game. I have a list of names. I need to decide what will my learning algorithm see. So you suggested to encode characters as numbers. Okay, but that's not enough. Still, I need to decide what properties of the input or the badge I'm going to provide to my learning algorithm. Here is a list of them. Some of them are numeric, gender, age, country. Could take many values. Some of them could be Boolean. Does the name contain the letter X? Does the name contain the letter X in the position 5? All these are Boolean features. Is the nth letter a vowel, yes or no? And so on. So basically, I'm taking the input, I'm encoding it somehow, and only then I'm moving to the learning algorithm. And already, hopefully, you see that there is some art in this process. Often it's hidden, but it's always there. There has to be some thought given to how you take input, the real world input, and give it to the learning algorithm. Any way you look at it, yes?
For that, what kind of feature would country of a person be? Would it be token?
Okay, so let's think about it. Let's assume I want a feature. So at this point, I'm still waving my hand a little bit, but that's a good question. So how do I encode the country of a person if I want to give this to my learning algorithm? Suggestions? Yeah.
There are multiple ways of doing it. One of them would be they just give one number to each country because there are only so many countries in the world, and then you can just encode them as numbers. Or there's a possibility that the function was actually a function of the letters of the country. So if the second letter in the country's name is a vowel, it could have been that as well. So it depends on how you want.
Okay, so let's take the first option because it's simpler. I have 500 countries, and I give them numbers. And basically, when you give me a name, along with the name in the badge includes country, includes a few other properties. I'm going to encode this as country equals 17. That's going to be my feature. So all the people that have country equals 17 have this feature the same. If you're coming from country number 18, it's going to be a different feature value. Yeah.
But doesn't that sort of imply in order to them, or the fact that country 17 and 18 are close to each other?
Okay, excellent. So let's go to the next slide and then go back to your question. So how do I do this? Eventually, my X, my input, is going to be some vector in a high-dimensional space. Let's assume now that everything is Boolean for a second. Let's take, all I want to do is I want to encode the country of a person. But I want to do it with Boolean features. How will I do it? By Boolean, I mean I have features that either take the value yes or the value no. Yes?
You have 500 Boolean values, and only one of them will be true.
Right, so when I'm encoding a country, I'm looking at these 500 variables. And for each person, one of them is going to be on, and all the rest are going to be off, because each person, let's say, comes from a single country. Okay? So that gives me a vector of dimension 500, because there are 500 countries. And the order matters. X1 is one country, X2 is another country, X3 is a third country, and so on. I need to know what X3 corresponds to, which country. And then this point, X1 up to X capital N in our example is 500, is a point in a 500 dimensional space that represents a person, the country the person came from. Okay, so that, now of course that's not going to be enough, so the first 500 dimensions of my vector are going to be the country, and maybe the next 2 dimensions are going to be the gender, and the next 5 dimensions are going to be maybe the height. The height I'm going to represent in classes. You know, if you are less than 4 feet, it's one. 4 to 4, 6 is another. 4, 6 to 5 is another, and so on. So I have a few ranges, and I'm going to use a few features for that, and so on. Overall, what I'm going to do is I'm going to have a point in some high-dimensional space that represents a person. And that's going to be the real input to my learning algorithm. Questions? Yeah.
Well, now that takes a lot of space to store it.
Yeah. True. It's going to take a lot of space. In fact, in a few minutes, we're going to get to an example that takes even more space. Space is something that we will have to think about. You'll have to think about it in some of the problem sets, but in almost all cases, yes. If you haven't thought about it, you know, we always think about 2 dimensions, 3 dimensions. If you're a physicist, 4 dimensions. In machine learning, you have to think about many, many dimensions. Because every point that you care about, every instance that you care about, is going to be represented as a point, typically in a high-dimensional space. Because we want to record many properties of this point. Okay, so again, we are waving our hands here a little bit, but hopefully you get the intuition that how we represent the input, the choice of features is crucial. If you don't represent specific characters in the names, along with their positions, this problem will not be solved. If all your feature space consists of is the height of the person and the length of the name and how many tokens are in the name, you will not be able to learn. Because the function does not depend on this, it depends on something else. So choice of features, what you are looking at in the input is crucial. Yeah.
So on the issue of dimensionality, so you mentioned, like, for example, physics, let's say it's 1 dimension. But, you know, in fact, right, it's actually the 1-dimensional problem that you have, for example, this continuous wave, can be understood as a very high-dimensional Boolean equivalent, right? You can say it's Fourier mode 1, 2, 3, 4, and so on. So the representation of the dimensionality also is very much affected by representation.
Completely agree, yeah. So the same Boolean space I could represent otherwise instead of Boolean with more bits. Yes, and we'll see examples of that. But But at this point, without getting into the detail, the message I want to send is representation is important. Okay, so that was X. Y, the label. That really depends on what problem do we want to solve. So do we want to solve the cases where we have just two possible labels, like this one, either plus or minus? Do we want to solve multi-class classification, like my email filing problems? I have 100 folders. For each email, decide which of the 100 folders it belongs to. Sometimes I have structured objects. So I want to segment this picture of a cat. It's structured because I want to know where the ear is, where the nose is, where the mouth is, and so on. And notice that not only it's a structure, I have to classify multiple things, they are not independent. Typically, the ear is going to be above the eye, above the nose. In a sentence here, where I want to understand the relation between the meeting and the leaving, which happened first? Again, I have some relations, and I have to label edges in this graph if you want, and there are some constraints on what I want to do. So if I look at multiple events, and I have event A and B and C, if I decide that A happens before B and B happens before C, I cannot say now that C happens before A. So I classify structure, and not all the outputs are legitimate. So all these could be labels, but there are many other options for labels. Labels could be continuous if I solve regression problems. So basically, I want my model to output a number between 0 and 1, say. Or I want my model to do ranking. Just decide whether x1 is better than x2. I don't care about the value. I just care about the order between them. Now, let's get to the model G, which is what are we going to learn? So in order to kind of think a little bit more about it and what kind of models we want to learn, let's play this another game here. So this is a learning problem, much simpler than the learning problem you solved last time. Basically, I already abstracted the input into 4 features: x1, x2, x3, x4. Think about x1 is whether the first name starts with an A, x2 is whether the second name starts with an A, x3 is whether the second character is B, and so on. Just 4 Boolean features. It's sufficient. There is, inside the box, there is some unknown function, f. And I'm going to give you a few examples. And I'm going to ask you, give me the G, your hypothesis. Here are 7 examples. First example is x1 is 0, x2 is 0, x3 is 1, x4 is 0, and y, the label, is 0. So what do you think the function is? Yeah.
x2 is 0 and x4 is 1.
And so x2 is 0 and x4 is 1 is the function. Let's check. If x2 is 0 and x4 is 1, then the label is 1, and otherwise it's 0. That's the suggestion. Does it work? Any objections? Works? Who says yes? Who thinks it doesn't work? Does it work? It works. Okay, so we found the function. You have some objection to that? Okay, so let's see. So we have a function that is consistent with these examples. Now, I have 4 bits, 4 features. You gave me 1 function. How many functions are there? How many possible f's are there on these 4 input bits. 2 to the 4, going once. Let's see. So before we count the number of functions, how many possible inputs are there on 4 bits? How many inputs? How many vector x's are there? 2 to the 4. So I can, you see here I gave you 7 examples, but it could be 0, 0, 0, 0, or 0, 0, 0, 1, all the way up to 1, 1, 1, 1. In each position I can put, I have 4 positions. In each position I can put 0 or 1. So I have 2 to the 4 inputs. Here are the inputs. Okay? So this is just 16, 2 to the 4 inputs. How many functions are there? What is a function? A function is a mapping from these 16 inputs to 16 y's, right? Because every input could have a different y. So how many functions could there be? Someone here said it? 2 to the 16. Why? Look at the rightmost column. There are 16 elements there. Each one of them could be 0 or 1, right? 2 options, 16 elements in a column. So 2 to the 16 is the number of columns that I could write. Think about it again. Each place in this column could be either 0 or 1, and they're completely independent. I can do whatever I want. So I have 2 to the 16 different columns there, which means I have about 65,000 possible functions. So we don't only have a lot of dimensions, even in small dimensions, we have a lot of possibilities. Now, yes? Why not 2 to the 4? It's true that there are 2 to the 5th rows if I wanted to write 5 bits, but that wasn't my question. My question was how many functions are there? So imagine the 2 to the 4 inputs. Forget the y column here. Just look at the 4 things, okay? These are the input. Now, one function will assign in the 5th column 0 to all of them, okay? Another function will assign 0 to all of them except for the last position. Another one will assign, so you see, I have fixed the 16 elements on the 4 leftmost columns. Every bit sequence on the right one is a different function, because at least on one of the input, it gives me something different, okay? Think about what is a function, right? At least on one of the input, it's different. So I have 65K functions. Now, really, in my learning problem, I don't have that many. Why? 1 second. I already gave you 7 examples, right? So look at the way I've written this rightmost column here. Some of it has, in my 7 examples, zeros and ones. Only 9 of them are question marks. So how many functions are still left? 2 to the 9 only, right? So 2 to the 9 is a pretty big number, it's 512, I think. And you found one of them. So very nice. One of the 512 functions, but you know, there are enough functions for each one of you to choose 3 or 4. So basically, what are we doing here? I mean, there are 2 to the 9 possibilities. How are we going to learn? All these 2 to the 9, the one nice one that you found is one of them, are legitimate outputs. Right? This was your objection, right? You said it's not unique. Yes?
So this is this is probably an under-constrained problem.
Excellent. This is an under-constrained problem. What does it mean we need more data?
So that we can say if the function is correct or not.
How much data do you need in order to say whether the function is correct or not?
9 more data would actually give us exactly unique function, but that's not what we.
This will be this, right? Right? Well, it's not really this because here I'll exhaust the X space. There's no learning problem. I just basically gave you a list of all the inputs. In learning, you will always be under constraints because this is a very simple problem, only 4 bits. All interesting problems you'll deal with will have thousands, hundreds of thousands, millions of bits because the input is expressive. And you will never see enough examples. So there'll always be the question, is learning possible? So that's the key puzzle that we have in learning. And the key solution is hypothesis space. We're not going to entertain all possible functions. We're going to entertain only function in a specific hypothesis space. Now, we can play a game now. This is basically just explaining what we said so far, so you can read it and convince yourself. H, the hypothesis space, is going to be a subset of this y to the x, in our case, 2 to the 16. Size of y is 2, size of x is 16. 2 to the 16 is the set of all possible functions. We are going to consider a small subset of it. And now we can play a game. We can say, you know what? I'm only looking for simple rules. That's my hypothesis space. What does it mean by simple rule? It's a conjunction of xi, nxj, and xk. I, j, k could be 1, 2, 3, 4, because that's my vocabulary here. No negation, so I'm not going to include your function. And these are my 7 examples. And if you try it, you see it doesn't work. In each case here, for each of these functions, I gave here a counter example of why this rule does not work. You can try more. You can try, you know what, let's take other functions. M of n rules. This is another set of functions. It's defined y is 1, the label is 1, if and only if at least m out of these n features is 1. Okay? So I have n features, in this case 4, but I can take a subset of the 4, only 3 of them, only 2 of them, only 1 of them. And I'm telling you, if m out of these are on, I'm going to say that the function is on. So I'm going to try this here. And in each case, I'm going to give you the set of variables and the counter example, except for one case here, x1, x3, x4. If 2 of them are on, that actually works, no counter example. So my function here is if one of x1 or x4 or x1 or x3 or x4 is on, sorry, let me start again. If 2 out of x1, x3, x4 are on, the function is on. On, I mean 1. And that works. Check, convince yourself. But what's interesting here is that it's not your function. It's different than your function. What does it mean that it's different? Suggestion, what do I mean when I say my function here, 2 out of x1, x3, x4 are on? This is a different function than the suggestion up there, not x2 and x4. What do I mean when I say the 2 functions are different? Yeah?
That you're subsetting a space by saying it has to be at least a certain number, but it doesn't say exactly what number it is.
That's true, but this is still a well-defined notion, right? So I said at least 2 of them. Look at all the examples. You'll see that in each positive example, at least 2 of these 3 is on. So it's a well-defined function. For every input, you know whether it's going to be evaluated to 0 or 1. but it's different than the function proposed at the beginning, and I want to understand exactly what do we mean when we say these two functions are different. Yeah.
Same inputs will always create the same outputs.
Okay, I think you mean the right thing. Let's say it in a slightly clearer way. So you say, I think what you mean to say is that there exists an input for which they will give me different answers. That's what it means, that there are different functions. Maybe they will agree on something. In fact, they do agree on these 7 examples. But at least on one of the remaining examples, they will disagree. That's what it means to be different as functions, right? And if you check, of course, you will find this. So what do I want to say this? One, success, we found a hypothesis, a consistent hypothesis. 2, for those of you, and I know that some of you think that this will be a class on neural network, it's a wake-up call. Don't worry, this is a neural network. Both functions, your function and my function, are neural networks. We can always write them this way, and we will see later on that these are neural networks, so everything is fine. This is a very, very simple example of a learning, of a hypothesis, of a neural network, if you want, but it brings home an important point, which is learning is an unconstrained problem, and we have to do something with it. So really, the way we can think about learning is as the removal of the remaining uncertainty, right? So if we knew that the unknown function was m out of n, or a conjunction with a negation, then we could use the training data to infer the single consistent function in this small class, small hypothesis space. But in general, we don't know this, so we have to choose a hypothesis space. And we can either choose a hypothesis space programmatically. I'm going to tell you, just use these kind of functions. We're going to do that, part of the class. Or we're going to let our algorithm bias the hypothesis space. And if you think about the learning algorithm as a search in this huge space of possible functions, 65,000 in our case here, we're going to bias the algorithm to not look everywhere, to just look for some simple functions, function with this property or this property. It's not going to try everything, because if it will try everything, it will find a lot of functions, and they will be different. And maybe it's not going to be useful for us. So we have to be ready for the fact that it's a big search problem, and that we could be wrong. It's not completely clear that the function that we find that is consistent on our examples, on our training data, is going to be the right one. Okay, so I want to stop here and tell you what we're going to do next. We're going to come back to this slide, which is thinking again about modeling, representation, and algorithms, and start with another example to talk about the modeling. And this is the example where we're going to start developing a generic algorithm. We're going to do this next week on Wednesday. Next Monday, instead, you're going to do Python. So this is a reminder. Next Monday is Python, and the recitation next Monday are also going to be Python. Before you're leaving, questions? Fine. Yes? Yes. Basically, yes. Yes. Okay, so looks like it's too noisy now. So just 1 second. Before we leave, any administrative question? Yes. No. No quiz this week. Yeah. It's on the website. Recitations are going to be announced on the website and on Piazza. Any administrative question?
When will the rest of the permits be issued? Throughout the day?
Some today and in the next few weeks, as slots are being cleared. So about 20 are going to be issued today. Yeah. Yeah. Okay, have a good weekend.
This is my last semester at UPenn, so
Okay.
I used to take this course.
Okay.
I am no waitlist, so I emailed you today as well, reminding you of my situation. Is there any way you could help me?
It's not going to help you. I mean, you can email me, but I think there are about 20 or 30 people in your situation. So, what category are you on the waiting list?
I think category 5.
What department are you in?
I'm actually from the Graduate School of Education.
Send me email. I don't know if it's going to help, but be patient. Wait a few more weeks, and then we'll see. It's definitely not going to help you today, but stay in the class, and we'll see what happens.
Is it like first come first serve? Because I.
No, it's a combination of some priority that the department sets, plus first come first serve. You were early on the waiting list?
Yes, sir.
Okay, so this will give you some advantage, but not a complete advantage. I'm sorry. But send me email. I'll check where you are.
Just to be explicit, I think this is like his remark. Like that 500 bits, you could just have one integer.
Yes.
Something that would decrease the dimension.
True. Only that it's not clear that it's going to help me. So really, the amount of information there is the same.
Right.
But you're right. So I think the point was very good, that is, you can represent things different ways. If I want to represent something with many Boolean variables, I can also represent it with single real-valued numbers or integers or perhaps other ways.
That's the benefit in the measure, because when you do the 500, the Booleans, right, the measure becomes clear because you do bitwise compare, right? You say they're the same country or not. Whereas if you go one-dimensional, right, perhaps you have the artificially kind of introduce a 1, 2, 3, 4, where the measure would not be useful.
Yeah, there are many other issues here. So some representation, for example, maybe I want to encode the system of names of countries in such a way that geographical proximity matters. So some representation will allow me to do it. Some representation will not allow me to do it. So maybe some algorithms can use Boolean input and cannot use real-valued numbers. So all these issues are going to play a role.
Okay. Thank you.
Sorry to be administrative a little bit. So I actually don't need the credit. I just want to audit and do the work without actually getting credit. Does that matter?
That's fine.
All right, cool. Do I need to, as an administrator, register for anything?
It depends on your department. Some departments require that, some don't. I don't mind.
Thank you.
We're not going to grade your homework.
That's fine. That's all I'm going to do is check the answer.
Yeah, but you will have to participate in class. Okay, good. So as I said last time, it's very likely that some of you will have to wait beyond the deadline. It's not a hard deadline. Nothing is hard. What department? It's not a hard deadline. So basically, you can always petition.
No, I can petition to have it taken on the, I mean, it's
Yeah.
technically a CIS course. I would have to petition to take it because I'm from a different department. But I cannot petition to add a course onto my roster after September 10th, is what she told me. So,
Ask again. I think it's possible. I think it's a university rule that you can petition to leave a class and enter a class with the signature of the professor even later. I mean, it's completely clear. Well, it depends where you are on the waiting list, but it's completely clear that it's not going to be completely resolved by the 10th. And the reason is that the drop date is after the 10th. So some people will drop it later, and then it will clear some spaces. So I typically urge people to stay on the waiting list and come to class for the first few weeks.
my advisor's advice is complete opposite. So that's why.
Okay, so it's your decision, not my decision. All I'm saying is that
Talking to CIS coordinate advisor of the program rules ahead.
So you can check with them what the rules are and in fact how to do it. But I know for sure that I've signed petitions a month into the semester. So maybe some departments disallow it, but I think I've done it for several departments. So it's not ideal, but it happens. And it's unavoidable because the drop date here, I think, is after the registration date. So yeah.
Thank you.
Hopefully that answers some other questions.
Yeah, Professor, I just added myself to the wait list today. Do you think it's still worth waiting?
Okay, if you edit it yourself, also on Piazza, go to Piazza
Okay.
and find a message that I sent on what to do if you're on the waiting list and you want to be in the class. Because so what happens is that a lot of people on the waiting list put themselves there in April,
Right.
and then they go to other classes and they don't care about it. So I ask people to renew their membership on the waiting list.
Oh, I see.
So look at the Piazza message and see, I ask you to send me a message with a specific subject, so I know that you actually won't take the class.
I see. I sent you an email today, so I'll send you another one.
So send it ideally with the specific subject because it goes to a specific folder.
Got it. Okay.
And I may not find your email otherwise.
I see. And I don't think I'm on the Canvas yet. Can you-
Yeah, so several people said that there's still a Canvas problem. I'll check it. Yeah, as of yesterday, at least for a little bit, it worked.
Right.
So we'll check it again today. I know that a few people are on Canvas.
So where should I get the homework for this Friday?
It's on the website.
Oh, it's on the course website.
Yeah.
Thank you.
Hi, Professor. Sorry for this. I'm a second-year PhD from Wharton Stats Department. I think one of my fellow PhD students come to you last week.
Yes.
And like we also talked this because my research is kind of involved into like measuring and stuff.
I got email from your
Although
I
also
think
we
your
talked,
department chair or school chair.
yes,
or
we
something
talked to
like that.
department chair and Wharton
Yes.
about this because our priority is really low on this, and we have really not many options in choosing courses. So I feel CIS is most related to stats, and we also like
Yeah, I know the story.
Yeah.
We'll see what happens. Basically, you have to be patient, just like because you're not number one on the priority list.
yeah,
But I think there's still a chance that you will get in, but I cannot tell you that it's going to happen this week. In fact, I can tell you it's not going to happen this week.
Yeah, but actually, like for Wharton PhD, the drop date is very early. It's different from undergraduate or master
know.
students.
So
That's why for us it's very important.
But it shouldn't matter. You can always petition.
But like we need a 3 credit to remain on F1 stage.
Nothing I can do. I mean,
see.
we have a huge waiting list.
I
Can
understand.
you tell us the number again? Like how many slots do you have?
I think now we have still about around 70.
So 70 on the wait list, and then you can enroll like how many numbers more?
I don't know. It depends on how many drop the class.
So if we want to be in the class, the only thing we can do is to finish the homework.
Yeah, just keep waiting, and I think it's going to take 2-3 weeks. And I can tell you that last year, at the end, we actually had 10 empty slots in the class. So there are 150 seats here, and we only had 140 registered at the end of the class because people kept dropping. So if you're patient, eventually you'll find a place, but some people are not patient. So there's nothing I can do now. I cannot register a lot more than the 150 because of fire rules.
So does it mean we can also late drop another class?
You can?
Like late drop another class once I get in?
Yes, you can always do this. I mean, so the law is very early, but you can always petition to do it. So it takes a little bit more paperwork, but it's doable. There's nothing I can do. I mean, so basically, I can add people only once other people drop. So today I added, we saved a few slots, so today I've added about 20, or people will get email later today. and then I have to wait that some people look at homework 0 and decide that they don't want to do it, or other reasons, and once they drop, we'll add more.
Okay. But another, but another question is how like for the category, do you know how many students are in the last category? Because
I don't off the top of my head.
Because like say if I want to transfer to the data science program, this is a requirement course, and also I'm originally in a system engineering program, and this is a requirement course also.
No.
So like
I know the
but we are
and
still in the last category.
You know that you are in category 5.
Yeah. So this is kind of like.
Yeah, but I think so. All of category 1 will be today already in the class, and maybe even most of category 2. So we are getting there, but I cannot give you a date.
Okay.
So there's no way we can move on in any category, even though we're.
No, but it doesn't matter. I mean, once slots are become available, you will get in, but I cannot give you any guarantee on when this is going to happen or whether it's going to happen.
Perhaps I can register for one independent study and then add this course.
You can do that to be on the safe side. Nothing I can do. I
Okay,
just
thank you
need
so
to
much.
wait
I
for
understand.
slots to open.
Yeah.
Thank you.
Yeah. Thank you so
Okay.
much, Professor.
Good luck.